Hey, welcome back. In this video we are drawing the shear force diagram and bending moment diagram of this cantilever beam that has 2 point loads. We have 20 kilonewtons pressing down halfway along the span, and then we have 20 kilonewtons pressing up at the end of the span. So what we need to do first is we need to figure out what the reaction here is at A. If you do the sum of forces in the y direction, 20 down, 20 up, we actually have 0 kilonewtons here for what we would call, I guess, AY. That's going to be equal to 0. There's no reaction force in the vertical direction, and then we have a moment here that we're going to call MA. And basically this force couple is 20 kilonewtons. Each force is 20 kilonewtons. They're separated by 2 meters. So the moment generated by that is just going to be 20 kilonewtons times 2 meters. That's going to be 40 kilonewton meters. That will be in that counterclockwise sense. So that means we're going to have a reaction moment here, MA, as the equal and opposite. So that'll be 40 kilonewton meters in the clockwise sense. Alright, so let's go and get our shear force diagram and bending moment diagram set up with grid lines at each point of interest, which is going to be the point loads here because there's no distributed loads, so we're just looking basically at the point loads. Alright, so now when we want to go and start drawing a Freebody diagram from the left hand side with a virtual cut just to the right of that reaction, we have this reaction force here. This is 0 kilonewtons. So we have where we have 0 kilonewtons, we're taking our virtual cut in this region. That means our internal shear is going to be 0. So the shear in this region basically from the support right up until the point load is going to be 0 kilonewtons. So we're going to drop that in just like that. Now once we get to the point where we extend a Freebody diagram just to the right of the point load, we're going to have to include this 20 kilonewtons pressing down. So now our Freebody diagram goes from the support at A just to the right of the point load. Then that means that we're going to have a shear force of 20 pressing up, or negative 20 in the downward direction. So where we have 20 kilonewtons, where we have a shear force pressing up to the right of a virtual cut, that's opposite our positive sign convention. So the sign of that is going to be negative. So we're going to come down here, and this is going to be negative 20 kilonewtons, so that's going to drop us down here. And then there's nothing changing in this region, so that's going to shoot straight across as negative 20 kilonewtons of shear in this entire region between these 2 point loads. So again, that's ending at negative 20. Now we do want to check to make sure that we've ended in the right place. So if we draw the Freebody diagram of the right hand side of the beam, taking a virtual cut just to the left, we know that we have this point load of 20 pressing up, and then we have to have some shear force. It's going to have to be 20 pressing down. Pressing down to the left of a virtual cut is opposite the positive sign convention, so that's negative sign, magnitude is 20, and that's exactly what we've got, negative 20 kilonewtons of shear at the end of the beam, so we've done this correctly. Alright, so now we want to take a look at the bending moment diagram. So the way that we're going to go about doing this is we're going to start off with a Freebody diagram that's going to include the internal moments. Whereas before, when we're doing the Freebody diagrams for shear force diagrams, we can really ignore the moments in these because we're just looking for the force balance that leads to the shear in those regions. But when we're talking about bending moment diagram, we need to include the internal moments, and where we're starting at a fixed rigid connection, then most likely the moment here is not going to, the internal moment is not going to be 0. It'll be some non-zero number. So when we put on all of our information here, we have AY, that's actually just 0 kilonewtons. We have the internal shear, which is 0 kilonewtons. And then we have MA, it was acting in a clockwise sense on the beam, which is 40 kilonewton meters. And then so we're going to have also some internal moment M. Now, talking about these 0 forces here that would form a force couple, even if these were non-zero numbers, we're taking our cut an infinitesimally close distance, or tiny distance away from the support. So even if these were non-zero, the moment caused by this force couple would still be 0, because as this distance tends to 0, the moment caused by the force couple tends to 0 as well. Now, so that just leaves us, that's all 0, that leaves us with our internal moment just to the right of this cut has to be equal and opposite to this applied moment then. So that is going to be equal to the magnitude of 40 kilonewton meters. And the sense is going to have to be counterclockwise to be opposite to that. Now when we look at an internal moment that has a counterclockwise sense to the right of a virtual cut, we say that's a positive moment. And so this moment here is going to be positive 40 kilonewton meters. Alright, so we'll throw that on up here, and then that's going to be 40 kilonewton meters. And then in this region, because the shear is 0 basically, and as we extend this dx to a distance of 1 and then all the way up to 2 meters, these forces here are 0, so they're not changing the moment as we go across. So the moment is going to be horizontal and constant all the way right up until we get to this point load here. Once we get to that point load, there's two ways we can look at it. We can add on the shear force here of 20, and then as we increase this distance past, basically from just to the right of this over, then we're going to be getting this force couple here with an increasing distance between them. Or the faster way to do it, instead of doing this stuff all in terms of x, is just to recognize that this shear force diagram has some area here, like we've been doing in previous videos, and the area here is just equal to the change in magnitude on the bending moment diagram, and this area is on the negative side of the axis, so that is going to push us towards our change in magnitude on the bending moment diagram towards the negative side. So this area here is base times height. It is 2 meters times negative 20 kilonewtons, and so that's just going to be 40 kilonewton meters. It's a change in magnitude, and where we have horizontal lines on the shear force diagram, it's just a nice linear change in the bending moment diagram. And then the magnitude is 40, so we go from 40 here, like that, 40 minus 40, right down to 0. And at the free end of a cantilever beam that doesn't have a moment acting right on it, we should be expecting the bending moment there to be 0, so we have done that correctly. The last thing that we could talk about really briefly is your prof might ask you to draw the deflected shape of this structure, and in this case it's actually going to come out horizontal from the wall there because of that fixed rigid connection. And then over the span of it, it's actually going to be bending up a little bit because the moment basically caused by this force about A is greater than the moment caused by this force, and that's going to tend this thing to bend up. And as long as you can just demonstrate that, yeah, I get that the end of this is going to be raised rather than going down, then you should be just demonstrating to your professor that you understand what you're talking about.